Hello and welcome back to Find, Solve, Explain. Today we're going to be doing the second question of the 2019 BMO2 paper. The question reads, for some integer n, a set of n squared magical chess pieces arrange themselves on a square n squared by n squared chessboard composed of n to the 4 unit squares. At a signal, the chess pieces all teleport to another square of the chessboard such that the pieces between the centers of their old and new squares is n. The chess pieces win if, both before and after the signal, there are no two chess pieces in the same row or column. For which values of n can the chess pieces win? Okay, first claim that I'm going to make is that every even value of n works. And I'm going to prove this like so. So if we look at this even-sided chessboard, not even squares, we can see that we can put the chess pieces, these green dots, on the long diagonal. And as you can see, there are no two chess pieces in the same row or column. Then we can move them all by one, basically, to do this. So in each, you can kind of split up. You can split up the chessboard into loads of 2 by 2 squares. So like this, and that continues. And each 2 by 2 square that was along the long diagonal like this goes to this. And as you can see, these still they still don't have any chess pieces that are in the same row or column. So this is a valid solution, and this will work for all values of 2. Okay, now for the odd numbers. Firstly, I'd like to prove by Pythagoras that if you have the distance between the centers to be odd, that means that one of A and B must be even, but exactly one of A and B. So if you kind of imagine the vector that the chess piece moves, and that vector has magnitude c, then we know c is odd, and we know that the components of the vector must add, the square of the components of the vector must add to an odd number. If you check the parity, odd plus odd doesn't work. Odd squared plus odd squared doesn't work. Odd squared plus even squared does work. Odd squared. And even squared plus even squared doesn't work. So we know that one of A and B must be odd, and this means that you must change color. Every token that moves must change color. So and that's because if you move an even number, you don't change the color, but if you move an odd number, you do. So in total, this vector that I was talking about changes the color of the token. This means that if you had A tokens on white squares before the signal, and B pieces on black squares before the signal, then you must have B pieces on white squares after the signal and A pieces on black squares after the signal. So that's a bit confusing, but it swaps. Okay. Next, I want to prove that for odd-sided squares where the long diagonal is white, the number of chess pieces on white squares is always odd. We can prove this by thinking about this square that I have on the screen now. So the diagonal has these green tokens, and we can make any possible configuration of the chess pieces by any valid possible configuration by moving the chess pieces either horizontally or vertically. So this one can move to here, let's say, and then fixing the problem. So if this one moves to here, this one must move here. And if you consider the sides of the rectangle, so if you draw the changes that happened, you can complete the rectangle, and you realize that when you do this, if this move is odd, this move must also be odd because it's a rectangle. Then they must switch colors. So basically, if this move is odd, then this move is also odd, and if this moves even, and this moves even as well. And this means that every time you change the color of one white square to a black square, another white square turns to a black square, and vice versa. So there's always going to be an even number of black squares, and therefore there must always be an odd number of white squares. However, this poses a contradiction to what I said before, because in this scenario, when we have an odd number of white squares, what we proved before said that we must then afterwards have an odd number of black squares. However, I've proved that this is not a valid configuration. So we're done.